Hello, everyone. Thank you for joining this webinar. Before we begin, I would like to ask you to please mute your microphones. If you have questions for our speakers, please type them in the chat. Each speaker can answer one question after his presentation, and we can discuss the remaining questions during the discussion. So now please mute your microphones so we can begin. I would like to inform you that unfortunately, the president of the National Observatory of Athens is unable to attend. However, he asked me to read on his behalf a short welcoming. Statistical seismology is an active field of research at the interface of statistical and physical modeling of earthquake occurrence and sequences. The societal importance of earthquake predictability and forecasting pinpoints to the fact that statistical seismology can have a major impact on the management of seismic hazard and risk, and thus to civil protection, and as such, it is a very important field for research. It is an honor for the National Observatory of Athens to host such an interesting event, organized by our colleague Katerina Orfanogiannaki and Ioannis Zoufras, and I await with interest the outcome of your discussions. So after this short welcoming, I would like to invite Professor Ioannis Zoufras, head of the Department of Statistics of the Athens University of Economics and Business, to say a few words.
It is a great pleasure for me. Thank you, Katerina, first of all. And it is a great pleasure for me, as the head of the Department of the Statistics of Athens University of Economics and Business, to host this important event for stochastic models and quantitative methods for earthquakes. The Department of Statistics is a pioneer in Greece, organizing a series of one-day meetings like the one we have today, conferences, seminars, and short courses. So after the successful event that we hosted on December about the implementation of statistical methods for COVID-19, I welcome this event with research from prominent experts of the field coming from Greece, Italy, Russia, and Japan. From the program, I can see important contributions of statistical methods implemented on earthquakes studies, including discrete time series, clustering methods, problem-specific models, Markov models, change point analysis, Bayesian methods. Before closing, I would like to thank Dr. Orfanogiannaki for organizing this exceptional event and Professor Karlis for helping from the side of our university. Without any further ado, I would like to announce the beginning of this one-day meeting on stochastic models for earthquake studies.
Thank you, Yannis, for the warm welcoming. Now we are able to proceed with our first speaker, Dr. Athanasios Gana. He is going to present us the seismotectonic characteristics and geodynamic effects of the March 2021 ongoing seismic sequence in Thessaly, central Greece. Thanasi?
Okay, great. So this work is still work ongoing because we only have 2 weeks of this sequence in northern Thessaly near Damasi and Tyrnavos, and the work is going presented here is a common work by a lot of colleagues by various institutes and universities, the University of Race, the observatory here from Geodynamics Institute and Institute of Astronomy and Remote Sensing, University of Athens, École Normale Supérieure, and Patras. So, what I'm going to present today is I'm going to show some new results identifying the main sources of the 3 earthquakes. The first one, the 6.3 earthquake that occurred on 3rd of March, the magnitude 6 earthquake that occurred on 4th of March, and the magnitude 5.6 earthquake that occurred on the 12th of March. To do this, I mainly use space geodesy observations of ground displacement, that is GNSS and INSAR. We model the sources of these earthquakes by inverting the displacement data, and then I will provide some information on the earthquake effects on buildings and the geo-environment. So the tectonic setting of this, let me make this, I think it's better now. So the tectonic setting of this sequence is located here in central Greece, in Thessaly, where you can see that this is an area of crustal extension, where the sigma 3, the principal stress axis, or the maximum extension axis of the strain ellipsoid, is roughly oriented north-south. The magnitude of this, as you can see from the dilatation map we see here, is about between 20 and 30 nanostrains per year. And as you can see, we can characterize this area of Thessaly as relatively low strain area with respect to other areas like here in Central Macedonia, over here, or of course further south, southern Greece. So further on this, we have the earthquakes occurring in the area where we don't have a lot of GNSS stations, but nevertheless, from the rest of the data we have now, it's relatively low strain. Again, I emphasize this important setting requirement. So in terms of geology, what we know is that there are a lot of faults, active faults that run in approximately east-west in the south part of Thessaly. On the north part of Thessaly, near Larissa, where the earthquake occurred, there are some known structures that deep to the north, and on the other side, deep to the south. So this is a basin that is roughly directed east-west and with of quaternary age. The older extension, I should say, direction is given by these structures here, like this one, and like that one, that is northeast, southwest. So the new structures are believed to be east-west, that is cross-cutting the old ones by an angle of about 45 degrees. So the first earthquake on March the 3rd occurred, as I said, in this area, northwest of Larissa. It was first associated with a known fault, is called Tirnavos. Later we found that on the same day that it was not that structure. And the majority of momentum solutions indicate northwest-southeast striking normal fault, either north dipping or northeast or southwest dipping, and at depths ranging, for example, between 10 and 12 kilometers, most of them. Later on, we had the next day, we had an earthquake of 6 on the moment magnitude scale, which was located a bit further north of the first one. And on the 12th of March, that's about a week ago, we had another 5.6 event, MW, I should say again, a bit further northwest of the second and the first. So an overall seismicity map from the NOAA revised catalog, showing also the location of the portable seismological instruments with these green triangles, and also showing the red stars of the main shocks, indicate an overall northwest-southeast cloud of aftershocks, with the exception of this cluster to the west of Larissa, which is relatively offset with respect to the main orientation of the sequence. In terms of evolution of the earthquake sequence, we see that there was, and I'm showing here some graphs with the rate of the earthquake occurrence versus time and the depth versus time, and we see that with the stars indicating the shocks with local magnitude of above 5.2, and this is the latest one occurring here. About 1,000 earthquakes have been recorded so far in the revised catalog. The depth distribution shows an average of events between 5 and 10 kilometers. So what is the data we use here? I'm going to present you the results. The first results today is that displacement maps from INSAR show that the deformation is spread over a large area of about 30 kilometers and comprises 3 distinct lobes. The first lobe is this one here, is the largest one, and it's associated with the first event, where you can measure about 13 fringes from the outer fringe to the inner fringe, and the direction of fringes indicates that this area subsided. So that's why we chose to name this sequence as the Damasi, and not Tirnavos, because Tirnavos is outside the deformation, and also that this fault here that's supposed to be the one that was activated was not finally activated, but the fault that is responsible for this main lobe is located beneath this this area, and is to the southwest of Damasi and north of Zarkos village. The next event associated with this lobe here, this is the main subsidence is located about 5 kilometers to northwest of Mesophori village over here. This is this event shows 4.5 fringes of deformation against subsidence. Whereas in the first case, we see that because of the geometry of the fringes, we can identify the fault deep as northeast. In this case, it's a bit more difficult because the arrangement of fringes is more symmetrical. So we don't know from this image if the fault dips to the north or to the south. And on the further to the northwest of this valley, where you can see here the loss of coherence because this is the Titarisios River flowing this way. On the northwest of this valley, we had the third event on the 12th of March with 2.5 fringes, more or less oriented east-west. Again, not clear at this moment if it's north or south dipping. So these 3 lobes are overlapping, and these 3 lobes are associated with separate faults. We can proceed further with the analysis and do the so-called unwrapping of interferograms. I'm showing here the coseismic interferogram of the second event, which shows a subsidence of about 14 centimeters along the line of sight of the satellite for the area of the Titarisios River. Titarisios River is here, flowing from north-south and then east. And again, showing this this lobe, characteristic lobe of deformation. Here is a cross-section. Also, it is interesting to see that the same interferogram captured some post-seismic motion along the first fault, the first earthquake fault that had occurred the previous day. So looking here at the cross-section, number 3, we see, for example, a small motion of 2 centimeters on the footwall. So this continuity on the fringe pattern is aligned with some evidence on the field I'm going to show you later. We can also proceed further and combine acquisitions from both orbits. So for example, here I show you a combined interferogram of the first and the second event. First event is here, second event is here. This is a descending orbit, so the satellite flies from north to south looking to the east. And we combine this information with another interferogram from the opposing orbit. We can decompose into vertical up-down and east-west component, and this shows again a huge area that subsided north of village Zarkos and south of Damasi, reaching 35 centimeters of coseismic and some post-seismic subsidence. Also, the area subsided here about, as I told you, about 12 to 14 centimeters. And east-west, the east-west component also shows that the hanging wall of this fault moved to the east, whereas the footwall moved to the west, with a considerable amount of motion of about 20 centimeters, as it was found here. From GNSS data, from the station that exists in nearby in the village Klokotos, this is a joint NOAA and INGV station. We can calculate the offsets of the antenna before and after the earthquakes. So this dot here indicates the position of the antenna on the east-west. This is north-south, and this is up-down. And the red line indicates the timing of the first shock, and the purple line of the second shock, the main shock. and then the position of the antenna stabilizes. So what we can see definitely is a motion, seismic motion to the west, about 3 centimeters, and to the south another about approximately 3 centimeters for the first earthquake. And for the second earthquake, we see a further motion to the south, whereas nothing really, it's within their of margins on the east-west component. So permanent crustal deformation was also recorded by GNSS. So this data can also be used in the version. There's no considerable motion on the up-down component on this station. This is 30 seconds data, and we process the data by using the precise point positioning approach. So we use this to invert for the ground source. This is all preliminary results. We're still working on this using an elastic hub space model of dislocation, which is rectangular, and we assume also uniform slip along this dislocation using the program in verse 6, which can be found on GitHub. So in the first earthquake, what we see clearly is that we can see all these, we can sample all these fringes. Definitely the area of the hanging wall is very rich in information. The area of the footwall is not so rich. Here with the red line, I show what should be the projection of the fault plane in the surface. So using this data, we end up with this fault, which is pretty rectangular, and this is only a first approximation, but fits very well the deformation on the surface. And it's clearly seen that this fault, if we can project this on the surface, it is projected over here, over the mountains. It's a mountainous area, and it has nothing to do with the Larissa fault, which is here, and the Tirnavos fault, which is further north. So this is a new structure. We can also model this, the evolution of seismicity using Coulomb, the Coulomb software of UAGS, and assuming again the same basic parameters. So for the first event, if we assume that this is a seismic fault here, which is blind, as I mentioned before, we can explain very well the cluster of aftershocks to the west of Larissa, and also the occurrence of the second event and the occurrence of the third event, because they're all located on positively loaded areas of the crust of the order of over 1 bar up to 0.2 bars in both directions. We also see that this area, the solution is at 7 kilometers depth, which, as I showed you before, is reasonable depth to approximate the seismogenic sources. And this is for receiving faults with that orientation, so low angle north dipping, and this is for high angle south dipping faults. And we also see that these huge areas of North Thessaly and Central Thessaly are located in stress shadows. So if we add also a fault plane for the second event, and this is the second event, and this is a solution now for optimal normal faults. That's why you see the stress shadows expanding, and you can also see that we have two solutions. One is for the north dip, one is for the south dip of the second source. So this is the surface projection of the fault plane. It seems like the north dipping modeling fits better the data, the seismicity data. We still have some stress transfer to the northwest of considerable amount, above 1 bar up to 0.2 bars at distances of about 15-20 kilometers to the west. Also, this area is highly loaded towards Larissa. Depth of damage, I show you some pictures. I've been to the area already 2 times. What you see is basically that most of the damage is associated with old buildings before the seismic code, like this one here. You can see in the village Amuri, contrasting example of a new building which is intact, an old one, which is characterized as red, which is going to be demolished. some cracks with a yellow sign indicating that it has to go past another, it has to be checked again on a secondary degree, as we say, and to be judged if it's going to be demolished or not. This is right on the epicenter of the main shock in Damasi. This is on the epicenter of this village is located near the epicenter of the second shock, as well as this this area near Lahoyani, where you see that we have a failure of the road, where of course the road is not the asphalt road here is not on bedrock, but it's been there was a fill by this material and the loose material, and then they construct the road, and because of the ground motion, the road failed. So this is out of use at this moment. It's interesting to also to observe in this particular photograph to the lower right, for people who are working with macroseismic data, this church, although located above the epicenter of the first main shock, suffer very minor degree of damage. In terms of geological effects, what we see is some spectacular features. This is the earthquake sequence of liquefactions. Here we see massive liquefaction and the south, to the south termination of the earthquake sequence near River Pineos. And here I'm sitting on the north part near village Vlahoyani. Tens of meters of craters, sand craters, where we have ejected material out. A lot of square meters of this spectacular phenomenon. And here on the right side, I see some gravitational cracks of about 17 centimeters I measured here, which are due to shaking, strong ground shaking of these embankments of River Titarisios. I should emphasize, though, that in this particular location, I found this surface crack. The surface crack indicates extension along the northeast-southwest direction, and this crack is aligned, as I wrote in the abstract, with the vanishing edge of the interferometric phase gradient of the first earthquake. In other words, this crack formed where the model from INSAR indicated that the fault is projected to the surface. So this crack is qualifying as a co-seismic surface break. However, there's no throw, and in places where I found throw, the throw is to the west, not to the east. So it cannot be characterized as tectonic rupture properly, but is definitely associated with the fault that generated the first event. Summarize my talk. I showed today that from INSAR data, there are three main laws of subsidence in this sequence of ground subsidence that are partially overlapping. The deformation pattern to us indicates the activation of three normal faults, which are previously unknown in this part. We had a lot of secondary phenomena with vast areas of alluvial deposits exhibiting spectacular liquefaction features. And we found no tectonic ruptures in the cases of events 2 and 3, that is March 4 and March 12, but we found a series of sporadic northwest-southeast striking surface breaks on the mountains north of village Zarko that are aligned with the surface projection of the fault that generated the deformation and the earthquake of March 3rd. And these geodetic data to us were crucial to locate the faults and constrain their geometry better. Thank you very much for your attention.
Thank you, Thanasi, for your very interesting presentation. Unfortunately, we have no time for questions. But if there are questions for Thanasi, we can you can type them in the chat, and we will have time to discuss them during the discussion. Thank you very much again for your presentation.
Thank you very much as well for inviting.
And we can proceed to our next talk given by Professor Dimitris Karlis. The title of the talk is Multivariate Count Time Series of Earthquake Data, Selection of Covariant Structure.
Okay, can you hear me?
Yes, we can hear you. We can hear
okay,
you.
I guess you also see my screen. So good morning to everybody. It's my pleasure to participate in this. I would like to thank Katerina for organizing all this. So I'm going to talk for something relatively different. So the idea here is that we do have sequences, actually the count, the number of events, and we would like to check what is the relationship between different areas on the number of events. So what is the scope here is that we have the number of events above a threshold in a given time period. So actually the threshold and the time period are perhaps some tuning parameters, and I'm going to discuss it a little bit later. And we do have the number of events from different areas. So actually we have a multivariate time series of counts, which is an interesting problem. There is some work on that from Katerina and myself, but it is still of quite importance, and I would like to contribute on that. So the purpose here is we would like to see whether the one-time series affects the others, in the sense that this creates some relationships, and perhaps we may consider whether the events in some area trigger events in the other area. But we would also like to check a little bit asymmetries, in the sense that what is the direction of the relationship between the different areas. That is why we are going to build a multivariate time series model, and then we are going to use some model selection in order to find the direction of the relationships. This is the map of the data I'm going to use. We do have, let's say, 3 areas in the North Aegean Sea. We have selected this example for this talk, and we would like to see what are the relationships between the events in between the 3 different areas here, and whether we can find relationships between the different areas. So if you see the events we have gathered are above a magnitude of 4, covering monthly periods from 1964 to 2008. And as you may see, the mean number of events and the variance are quite different, implying some sort of over-dispersion, which we have to take into account from our model. So this is, let's say, the data. So you see the number of events across the years for the 3 different areas. And we would like to see whether there are some relationships between the different areas. Okay, so this is a cross correlation, and this is, let's say, an interesting plot, in the sense that we see that the time series are indeed present. So we do have, let's say, some sort of autocorrelation. And the plots here are the cross correlations. So actually we see that there are significant cross correlations between the different areas, which means that it is a good idea to model together jointly by a multivariate model. The challenge is some kind of triggering effect. So the idea is that if we have, let's say, just 2 areas, and the number of counts in area 1 at time t and area 2 at time t are the number of earthquakes in each area, we would like to find things like whether the events for the first area at time t relate to the events of the other area sometime before. Okay, so this is, let's say, the idea here. Okay, so let's start with some technicalities. The idea is that we have counts. We need to define time series for counts. So in every, let's say, statistical course on time series, we do have autoregressive models, but actually we cannot fit them here because we have counts, which means we have small integers, and all the models based on Gaussian assumptions perhaps cannot be very helpful, especially for low counts, as it is the case here. So there is a model back to 80s that mimics a little bit of the regressive models. So actually, instead of this multiplication here, we have this operator, which is called the thinning operator. And actually, this operator here makes possible to have an integer value here. So the model is based, mimics, let's say, the regressive model for the one, plus some innovation term here. So this term here is called the binomial thinning operator, and actually implies that if we write something like that, the random variable follows a binomial distribution with a number of trials x and probability of success alpha. So there are plenty of extensions of this kind of thinning in the literature, but I will use this thinning operator today. So the idea is that we have here, let's say, a binomial random variable plus a discrete distribution here, which gives us an integer value here. So we have, let's say, a properly defined model for integers. The sequence epsilon is called the innovation process and has a finite mean and variance. And based on that, we can derive all the properties of these models. For example, we know that the mean depends on the mean of innovations. We also we can prove, for example, that autocorrelation is exponentially decaying, which means that we do have autoregressive-like structures, and that's why we call this the integer autoregressive model. Of course, in our case, the interest lies on many dimensions. So we define a model which is called the multivariate integer autoregressive process. So actually now xt is a vector of different values at time t. So actually we do have a lot of time series. Each one is a count time series. And actually we try with this, let's say, definition here to put all them together. Alpha is an n times n matrix. So we assume here that we have n different time series. This is not a covariance matrix. So actually this is a matrix that satisfies some other properties. And for stationarity, for example, we must have the maximum eigenvalue of this matrix to be lower than 1. And of course, this is here the binomial thinning, and we apply the binomial thinning in the same way as we do matrix multiplication. Okay, so this is what we propose here. Note that by defining matrix alpha this way, we assume that for each time series, the current value depends on the previous one. But not only for this time series, but for all of the others. I will show you in a minute. So this is the basic model that we are going to use. Of course, the innovation term here is a multivariate discrete distribution, and actually it has some covariance matrix like that, and we assume that the mean is this one. So actually we assume that the innovation term has a finite mean vector and a finite covariance matrix. Okay. Based on that, we can derive interesting properties. It is not my purpose, let's say, here to discuss in detail all these properties. Perhaps this is not the purpose here. But the idea here is that the marginal series, so actually each series separately, is not anymore autoregressive, but it is, let's say, an integer autoregressive. Yes, it looks like an ARMA model of orders n minus 1, but in the discrete case. Let's say this is in ARMA. Okay. And another interesting thing for my application is that if we try, let's say, to estimate such a model, we can use conditional maximum likelihood approach, in the sense that we can write down the conditional densities. At a first glance, the conditional densities are computationally very intensive because we have a lot of finite sums, but in practice we can simplify a lot and actually make it tractable even in, let's say, dimension of 10 or 15. So this is, let's say, the way we estimate parameters by some kind of likelihood. So this is the conditional likelihood with condition on the past. So far, I have defined only models of order 1. Okay, but actually you may see that if I come to the basic definition, I can add, so here I relate t times t minus 1, but actually we can add more terms here in order to define inner multivariate inner p processes. Okay, so for example, I mentioned that we do have tricks to simplify the calculations, and another reason is that most of the sums here are convolutions of binomial distributions. We know from theory that convolutions of binomial distributions are extremely simple to calculate because it is just product of polynomials, and we do have very accurate and very quick algorithms to derive something like that. So actually, the order of finite summation is typically a very simple polynomial multiplication plus one sum. So actually, we need to, let's say, derive just one sum because all the other calculations are much easier. Okay, so in order, let's say, to go a little further, we can relax some of the assumptions of this model. And for example, we may assume something like a diagonal matrix alpha, which means that we have less, let's say, structure, but also we may assume uncorrelated innovations, which is also, let's say, quite helpful to decrease the calculations. Okay, so let's see a little bit an idea. So, for example, in the bivariate case, the model says something like that. So, bivariate case means that we do have just this time series. So, actually, what I'm saying here is that what I'm going to see for the first series at time t depends on what has happened for this series at the previous time point, plus what has happened to the other time series at the previous time point, and the same for the second one. So actually the interpretation of the parameters alpha is something like that. And that is the interesting thing that we can relate between that. Okay. So we do have some parametric cases here. The first one assumes a bivariate Poisson distribution, or we can assume, let's say, some other properties. For example, this is the non-diagonal with bivariate Poisson, the diagonal with bivariate Poisson, and so on. One interesting point here has to do with model selection. So the idea here is that we need to know which terms of the matrix alpha are those that really contribute to the model. So the model selection I mentioned relates exactly to this problem. So we need to take care of the different parts of matrix alpha. In my point here, I need to know which ones of these 4 parameters are really needed, or perhaps we can decrease the number of parameters by removing one of them. So this is the kind of model selection. So let's see what's going on with our data. So to start with, this is again my data set and the plot that we have already seen. The idea here about the triggering effect is that, for example, if I remove this term here, I assume that the second time series, the second area, does not take input from the first area. But while the first area takes input from the second one. So it seems that there is some directional relationship. So the second area, let's say, introduce some relationship to the first one, but not the other one. And this is the interesting about this model. Okay. So in our case, we do have 3 areas. So the model can be written in the full version like that. So we do have 9 parameters, and we assume here that all parameters are present. So all kinds of relationships are present between the different areas. And we assume also Poisson innovations for the model. In order, let's say, to see which ones we need, we represent every model as a vector of 0 and 1s. So actually the model with all 1s implies the full model, while the model which is a diagonal is this one. So actually we assume zeros for the different non-diagonal alphas. That is why we do have 2 to the power of 6 different models. Note here that we think that the smaller model is the diagonal one, in the sense that we know that we do have time series. So this actually implies that we do have 3 parallel time series and no connection between them. Okay, so that's why the diagonal elements are always present in the model. So an interesting point here is that the likelihood ratio test is not the typical one, because let's say the nested models imply values in the boundary parameter space. That is why we cannot use the standard likelihood ratio test to check between models. And we have derived the asymptotic distribution of the likelihood ratio test, which is actually this one. So actually it is a mixture of different chi-square with different degrees of freedom. And we will try to do this. So the null distribution, for example, is a mixture of is a degenerate distribution of a chi-square with 1 degree of freedom and chi-square with 2 degrees of freedom. And we have done some simulations to verify this asymptotic result. So here you see the asymptotic result. The red line is the assumed distribution, the asymptotic result, and this is what we get from the simulation. So actually we have verified what's going on here. So with respect to the fitted models, here you see the 64 different fitted models, and it is quite interesting that you may see that there are some models that are perhaps much away from the other ones, while we may see that here there are some models that provide quite interesting log likelihood. So actually it is a good idea to see which are the terms in these models in order to verify which are the good let's say structure for matrix alpha. If I focus down here, you see that the models, most of the models, all the models have the ones here. So actually these are parameters that they contribute the most. And if you see the last 4 models, those models are not statistically significant if we use likelihood ratio test. And this model, the great model, is the best model in the sense of the best I. So actually this model implies that there are 2 parameters here, 2 alphas, that they do not contribute, and perhaps we may remove them from the model. So if you check a little bit the presence or the absence between the different parameters, this is an interesting thing here, because for example, for parameter alpha 2, 3, you see that when it is present, the likelihood is much, much higher. While for parameter alpha 1, 2, you see that the difference is quite small, even if it is present or not. This implies, for example, that some parameters are very important, more important than the others. So for the selected models, the selected model is this one. So actually we do have 2 parameters set to 0, this and this. We have the alphas like that. So it is interesting to see that the alphas are quite big in the diagonal, implying that we do have time series and we have to account for this in any case. And these are the lambdas. These are, let's say, the mean. This relates to the mean of each series. The zeros here can be interpreted that area 3 does not trigger area 1 and area 1 does not trigger area 2. So actually we have found this kind of directional things that we would like to investigate. And in order, let's say, to wrap up, it is interesting here, but perhaps this is a very nice and interesting discussion to interpret why those areas are connected and those are not, while there is this directional, let's say, finding. Of course, I presented only results with one time unit, which is MAM and threshold 4. We have done some work on this because actually it is nice to see whether we do have some scaling with respect to time and threshold. In some of the cases that we have checked, the results do not change in the sense that we still find zeros here, but actually a nice problem here is to identify some kind of optimal threshold and time window. We have also checked, but not in very detail, some model of orders too, in order to see whether the time distance must be more than a month, but we didn't find better results. That's why I present only here the order 1. We do have some work on model selection based on Bayesian model selection through transdimensional out-of-10 Monte Carlo. And we have also some more work on how we can improve the computations in order to go to higher dimensions. I mean, for other applications, not for earthquakes, we have run up to dimension 10, but actually here, dimension 10, if we try, let's say, to take 10 areas together, perhaps this is too much because it is very hard to interpret what's going on and it doesn't make sense, let's say, to have so many different areas related at once. So, as a conclusion, I think that this is an attempt to fit a lot of time series of earthquake counts together, and this model offers some ideas about the triggering effects. Also, it's of note that these models mimic the vector autoregressive models, so some literature still applies with respect to selection of covariance matrices and all these type of things. That's all from me. Thank you very much. The floor to Katerina.
Thank you, Dimitri, for your very interesting presentation. There is a question for you in the chat by Jiankang Zhuang. He says that it would be nice to check whether epsilon and he are correlated for all t or not, in order to see whether a higher order regression is necessary.
Yes, okay, that's true. I didn't mention that we assume that epsilon and x's are independent, but actually one may extend and complicate a little bit the model by assuming some kind of relationship between them. Of course, it is not that easy to derive such a model, but this is something that there are some attempts in the literature so far. So thank you very much, Ron.
Thank you, Dimitri, very much. And so now we can proceed with our next speaker, Professor Jiankang Zhuang. He will speak about how focal mechanisms can be incorporated into the ETAS model.
Good morning, everyone. I'm Zhen Zhuang from the Institute of Statistical Mathematics in Tokyo, Japan. I thank Katerina for inviting me to this nice webinar, and this time I will report my work in recent years with my student, Eli Maita, in study on how to extend the ETAS model to the domain of focal mechanisms. This talk is divided in 4 parts, and the first part is the ETAS model and decluster, and then I will say something on how to represent focal mechanisms, and then focal mechanism distribution for background seismicity and for earthquake clusters. At last, I will say something about how to incorporate focal mechanisms into the ETAS model. Here, I assume that everyone here is familiar or knows something about Yoshi Ogata's ETAS model. The conditional intensity, also named as time-varying seismicity rate, is written as a sum of the background rate mu and the aftershock rate triggered by each event in the past. The background rate mu is a function of location, but it's a constant in time. In the triggering part, the positive exponential function kappa is the expected number of direct offspring from an event of magnitude A, m. The positive exponential function means that big events triggers more aftershocks. The occurrence time and location of the aftershocks follows some inverse power law. This is the O'Murray formula, and this is another two-dimensional inverse power law. Given an K-log, we can fit the K-log with the ETAS model to obtain the model parameters. Once we have the model parameters, we can then calculate the probabilities that an event is a background event, or it is triggered by a previous event by those two formulas. Here I refer the detail of this technique to my paper in 2002 and 2004. Now we go to the part on the representation of Fulcrum mechanisms. The Fulcrum mechanism of an earthquake describes the deformation in the south region, how the seismicity, the seismic wave generated. In the case of the fault-related events, it refers to the orientation of the slipping fault and the slip vector. Slipping fault and the slipping vector here. And it is also known as the fault plane solution. According to the relationship between the slip direction and the strike direction, Fulcrum mechanisms are divided into three classes: strike, slip fault, normal slip fault, and reverse fault. Seismologists always use a beach ball to represent Fulcrum mechanism. Between those two possible planes intersecting through the beach ball, one
μοντέλο πρόβλεψης σεισμού και πλαένας τιμές.
Sorry, Zhuang, I think I have muted you by mistake. Sorry. Sorry to interrupt. Just give me 1 minute to open again.
Okay.
No, I can hear you. So yes, you can continue. Sorry.
Okay, no problem. And so this is the I just say from between the two possible solutions for the Fulcrum mechanism of the fault plane, we cannot distinguish them from the seismic wave solution. That means we don't know which one is a true fault plane and which one is the auxiliary plane from the seismic wave solution. Fulcrum mechanism can be represented in absolute manners or relative manner. So there are four types of absolute representations to represent such kind of double coupling Fulcrum mechanism. One is we just use the angle of the strike angle, the dip angle, and the rake angle of the for the slip vector. And we can also use the vectors of the fault plane and the slip vector. For this way, the next thing for this presentation is we can use different combination of those kind of vector to show the downward representation, the handward representation, or the downward representation of the auxiliary plane. So this is quite nice representation too. And of course, many people also use vector presentation for the p-axis, the pre-axis axis, and the t-axis, that's the tension axis, and also the null axis. So it is a null axis corresponding to the intersection of the two fault plane here. The most complete way to represent the Fulcrum mechanism is moment tensor. Moment tensor can not only represent the double coupling, but it can also describe all kinds of Fulcrum mechanisms. And in this work, we use a relative representation. We first choose a reference Fulcrum mechanism. For example, we can choose a strike slip fault with vertical fault plane and a strike to the north. Any Fulcrum mechanism can be represented by a beach ball, can be obtained by rotate this the reference beach ball with a certain angle about a certain rotation pole. The angle is so-called Kagan angle. This Kagan angle can be also regarded as a distance between two Fulcrum mechanisms. Such a rotation can be represented mathematically by a rotation matrix. But more conveniently, we use the unit quaternions to do the work. The real part of the unit quaternion is related to the rotation angle by so it is just the cosine of half of the rotation angle, and the imaginary part is in fact the unnormalized direction of the rotation pole. When rotate the reference beach ball to have the same pattern as an arbitrary Fulcrum mechanism, what's the probability distribution of the rotation angle? This is called the uniform distribution of the Kagan angle. For different requirement of the rotation, the probability density is different. When we require that not only the fault plane of the initial Fulcrum mechanism, but also its down wall and up walls must be identical to those of the final target Fulcrum mechanism. This is called DC1, means there is no symmetry in the rotation. This density of the rotation angle is shown by this black curve. So if we require only the fault plane must be identical. So, but we do not mind whether the down wall of the initial Fulcrum mechanism is rotated to the upper wall or the down wall of the target fault plane. So this is called the DC2 plane. That means the fault plane is known, but which side or not, we don't mind. The probability density is shown by this red curve, and we can see here the peak value is at 90 degree. When we don't care whether the starting fault plane is rotated to the target fault plane or the target auxiliary plane, so then this is called DC4 symmetry. That means neither the nodal plane and the sides are distinguishable, and the probability density curve is represented by this green one. So it's the peak value is still at 90 degree, but there is a kind of discontinuity part in the first order derivative is around 190 degree. The data here, we are going to study the data in FNet data recorded by the National Institute of Earthquake Disaster Prevention in Japan. So this catalog gives almost all the focal mechanism of earthquakes above magnitude 4. So we select the events above magnitude 4.2 from the year of 1997 to 2014. So for each location to show the distribution of focal mechanism, we need, of course, a reference focal mechanism. Here, we choose the reference focal mechanism to be the mean focal mechanism nearby in the local area So the rotation angles between each earthquake focal mechanism and the local mean focal mechanism is considered. So the problem is, how can we obtain the local average focal mechanism? Here we use a smoothing algorithm proposed by Kagan and Jackson in 1994. In this formula, MPQ is the normalized moment tensor. That is, the moment magnitude is normalized to the fixed one. For each event, 3 weights are used. This f of r is a function of the distance from the current location to each earthquake. Please note this f is not the spatial response function in the ETAS model. I apologize for the abuse of the notations. So d here is a function of the angle between the earthquake fault plane and the direction connecting from the earthquake to the static region. And W is the weight for the magnitude. This means a large earthquake have a larger weight. And using the Kagan and Jackson method, we obtain the local average focal mechanism for all the Japan regions. In the left panel, the red, green, in the red one normal faulting, blue ones thrust faulting, and green ones a strike faulting. So this figure shows that the tectonic structure and stress field in the Japan region is quite complicated. The right panel shows the histogram of the rotation angles are quite different from the uniform rotation. It means the focal mechanism in each local area has a distribution like a Gaussian distribution, with the mean being the local average and a deviation of the rotation as a corresponding rotation angle. Now we check the focal mechanism of the background seismicity in the earthquake cluster. And so remember in the ETAS model in the introduction part, when we use the ETAS model to fit the data and obtain the model parameters, then we can obtain the probability each event is a background event or it is triggered by one of the previous events. So from those 3 formulas, we can see that each earthquake is sliced into many small slices. So each slice belongs to the background or belong to one of the previous events. To investigate the property of the different kinds of earthquake, we need only put the slices belong to the same category together and then make the calculation. For example, if we put all the omega j slices together, then we have all the background events. The slice is just for describing, and in the real calculation, we just give different weight for each event. When calculating the local average focal mechanism for background, we just need such a weighting. So what we do is we only slightly change the Kagan-Jackson algorithm. We put the background probability as the first weight in the smoothing formula. Similarly, when we calculate the histogram of the rotation angles in order to get the probability density, we also put the weight for each event. So this function here, I, is a logic function. So if the statement in this inside the bricks is true, I takes value of 1. Otherwise, it takes value 0. So the weight histogram obtained by this formula can be regarded as the probability density for the rotation angles, for background, for seismicity, for background focal mechanisms. And those figures are results for the background seismicity. The histogram of the rotation angles is in the right panel. So we can see for the background focal mechanism is slightly more concentrated to the local average than the total number of events. And then we consider the triggered events. For triggered events, that means non-background events in the cluster. So the reference focal mechanism is very easy to choose. We use mother events as the reference to calculate the rotation angles. Here the weight here is the triggering probability. When plotting the weighted histogram, we apply this formula to all the possible pairs of I and J. And in the final results, the distribution of rotation angles for the triggered events is similar to the background events, but is more spread out. It's the large angles, and slightly more concentrated is small angles. So then we have done some statistical tests to see whether those kind of distributions are different or not. The conclusion is yes, they are different. And now we extend our ETAS model to the domain of focal mechanisms. We first look at the relationship between the focal mechanism distribution of the triggered events and the uniform rotations. So this right panel shows the ratio of the distribution for the rotation angle distribution for the triggering pairs to the uniform rotations. And we found such kind of such ratio can be nicely approximately by a double exponential function. So in this way, we can extend our new ETAS model to the domain of Fulcrum mechanism in this form. So here I use phi to denote the Fulcrum mechanism. For all the events, the distribution of Fulcrum mechanism can be expressed as the distribution of those rotation angles. Delta means rotation angles between the two Fulcrum mechanisms. And for the background seismicity, the reference Fulcrum mechanism is the local average Fulcrum mechanism here. And for triggering events, the reference magnitude is the mother's Fulcrum mechanism. And the probability density functions, both of them can be expressed as the density of the uniform rotation multiplied by double exponential scaling factors. Here we introduce 4 parameters, A1, A2, B1, and B2, taking consideration of normalizing the totally 2 independent parameters newly introduced. So let's come to the summary. So first thing is correlation exists between the focal mechanisms between the mother and upstream events in earthquake clusters. So these results can be also seen in the first talk of today. And focal mechanisms can also be incorporated into the ETAS model. The third conclusion is I use stochastic construction to build a proper form of the new ETAS model in this study. We need to still do some future work. One thing is whether the rotation poles are uniform distributed or not. And we also need the implementation of the new ETAS model in computing program language. Thank you.
Thank you.
Yes.
Thank you, Frank, for your talk, for the overview of your work. Unfortunately, I had some internet problems, and I was
I see.
I was out. I see that in the chat there is
some questions.
I see maybe Dr. Gerasimos Kouliaras would like to ask the question, because I see something in the chat, but for me, Dr.
Yes, please, Gerasimos. Oh.
No, actually, I just applauded. I was very happy with your talk, and I just clapped.
Sorry, for
Thank
me,
you very
just,
much.
Thank you.
Yeah, I cannot see the anime. Thank you, Gerasimos. Thank you, Zhuang. I'm sorry.
Thank you for the talk.
I lost the connection. So if there was another question in the chat, if someone
I'm sorry, I forgot to open my video. Okay.
So thank you, Zhuang, very much.
Thank you
for your talk. And now we can proceed with our next speaker, is Rovi Liku, and her subject is change point analysis in seismicity modeling. Rovi, if you are ready. Thank you. We can we can see your screen. You may begin. Thank you.
Good morning. I would like to congratulate the organizers of the webinar for this initiative. I'm going to talk on change point analysis in seismicity modeling. This is a common work along with my supervisor, Professor George Aklidis. As far as the outline of the presentation is concerned, an introduction with the mathematical background of change point analysis is provided, covering hypothesis formulation, parameter estimation, and methods of statistical hypothesis testing. The main body consists of a brief review on change point analysis in seismicity modeling and a simple application on real data. In conclusion, concluding remarks, future perspectives and references are quoted for further discussion on the issue. The appendix provides some extra supportive material for a more detailed approach, in case it is needed. Now, we shall proceed in hypothesis formulation. Given a vector of observations T, T1, T2 to Tn belonging to Rn, which usually represents the occurrence time points of earthquakes, it is questionable whether all data are identically distributed according to a common distribution of constant parameter vector theta belonging to Rn. All their distributional parameters are subject to changes. The assumption that the parameters are piecewise constant can be adopted when abrupt changes are observed in the dataset. In the latter case, it is assumed that there is a vector of indices τ, τ1, τ2 to τk, where τj is less than τj plus 1, which are usually time or time step indices, at which parameters change, and there exist different parameter vectors θ1, θ2 to θk plus 1 belonging to Rn, suitable for their different parts of the data. Thus, the hypothesis formed can be expressed by means of the likelihood function. According to the Null hypothesis, the data set supports a likelihood function of the form P of t given theta, where t follows F1 distribution. Otherwise, the data supports a likelihood function of the next form, conditional on the separate parameters. In a frequentist approach, the parameter set is usually estimated through likelihood maximization. In a Bayesian approach, the estimated parameters are considered random variables with prior distributions, and thus, according to the well-known formula of the Bayes theorem, the posterior distribution of whichever sort parameter theta prime is calculated as following. The parameter estimates are the posterior modes, which are computed with the marginalization of the joint posterior distribution. Accordingly, hypothesis testing is conducted with the Bayes factor, which accounts for the ratio of the hypothesis posteriors, expressed by the equations below. These are the posteriors of the two models. For the selection of the most suitable model, Cat and Raftery suggested that the null posterior be at least 100 times smaller than the posterior of the alternative hypothesis. Likelihood ratio tests may also be employed. In this case, it is tested whether the ratio exceeds a threshold that depends on the nature of the likelihood function and the significance of the test. Information criteria and non-parametric tests are usually involved too. Examples of them will be provided later on the grounds of the quoted application on real data. Concerning methods of search for change points, at most one change point may be sought in the whole dataset. Binary segmentation suggests the application of a test for a single change point over the whole dataset, and then, if a change is detected, the successive application of the same test in the segments created before and after the current change point, until no statistically significant change points are found. Dynamic programming techniques have been involved to guarantee the best possible segmentation. Maximization of posteriors in terms of Bayesian approach for a single or multiple change points have been suggested as well. Concerning some fundamental seismicity models, changes have been detected in the lambda parameter of the Poisson process within the Bayesian approach for a single and multiple changes and the likelihood ratio test. Theta parameter vector is the epidemic type after theta parameter vector of the epidemic type after subsequence model with the employment of information criteria. B value of the Gutenberg-Richter law within parametric and non-parametric framework or lacking statistical hypothesis testing. There are alternative parametric techniques regarding monitoring zeta scores of the general form zeta I equal to xi minus the mean of sigma, where sigma is the standard deviation of the sample. References in the parentheses are such examples. They are well known enough. Changes of the parameters in Dirichlet processes with the Bayesian approach as well, and changes of multifractality parameters of pseudo-velocity defined as the ratio of the distance between two successive earthquakes over the inter-event time with the likelihood ratio test. Non-parametric tests have also been used. For example, the two-sample Kolmogorov-Smirnov test has been introduced to change point analysis on the inter-event time between successive earthquakes for the definition of the time period of completeness for an earthquake dataset with magnitudes above a fixed threshold. Randomization tests have also been involved in search of changes in network parameters when network theory was employed in the study of foreshock and aftershock sequences. Change detection without statistical hypothesis testing has been employed too, covering region time length algorithm, pattern informatics, M8 algorithm, which deal with parameter monitoring mainly. Markov models, like simple Markov models or hidden ones, or filtering techniques involve a transition from one stage to another, and this may imply parameter changes in the model. Now, an application on real data is presented. It is a common study along with Professor Chaklidis and Professor Eleftheria Papadimitriou. We performed change point analysis on the seismicity in the Gulf of Corinth, Greece. This is one of the most active areas in Greece, seismically active, of the data set of earthquakes with magnitude greater than or equal to 3 that occurred during time period 1964 to 2017. In Figure 1, we can take a look at the epicentral distribution of earthquakes with moment magnitude greater than or equal to 4.5, above which the dataset is complete, that occurred in the study area during the time period 1964 to 2017. Changes were detected in the mean and the variance of the inter-event time between successive earthquakes with offline and online approaches. Within the offline approach, non-parametric Bruns exact linear time algorithm was employed. This is a dynamic programming algorithm, and SWOT information criterion and the minimum possible segment length were selected. SIC is expressed as following. Theta d denotes the whole set of estimated parameters. Its cardinality is d, and the change point is also considered an estimated parameter. That's why we put here d plus 1. I think you can see my cursor. I hope so. Online detection involved a mock method and SIC, and it was based on a Lepage type non-parametric test of the following form, where M is the mood test statistic and T is the Man-Whitney test statistic, so that M concerns the scale of the data as it is obvious from lambda k term here, where N is the number of observations and Rxi represents the rank of Xi. Accordingly, Man-Whitney test statistic is expressed as following. It is the well-known statistic. And it detects changes in the mean of the data. Figure 2 depicts occurrence frequency, the inverse of the occurrence frequency, because we are mostly interested in the active phases of the data, as a function of earthquake serial numbers, and presents the primary results of the offline analysis. Horizontal bars represent the estimated means between successive change points that were detected offline. Diamonds stand for strong earthquakes, that is, earthquakes with magnitude greater than or equal to 6. This analysis suggested the division of the dataset into 12 segments, defining periods of about 0 mean and small variance, and others of increased mean and variance. The colored ones are the ones of increased means. In figure 3, figure 3 is the same as figure 2. That is, it depicts the inverse numbers of inter-event times. The dates when the change points are estimated online now are noted over the change points. The dates in parentheses are the dates of the detection time. In subfigure B, vertical lines at the change points and the detection time suggested by the online change point analysis are drawn. Solid vertical lines stand for the estimated change, while dashed lines represent the detection time of the change points. The results of the online approach are in accordance with the offline one. The detection time points are only a few observations far from the change points. You can see it here. They are about 6 observations far. The onset of a phase with increased activity takes about 60 days to be detected, while the onsets of the quiet phases need about 1 year to be detected. The autocorrelation function of the occurrence frequency over the whole dataset is presented here. Dashed horizontal lines represent the 95% confidence interval for the hypothesis of zero autocorrelation. Thus, weak autocorrelations are observed, indicating dependencies in the dataset. On the contrary, in figure 5, we can see the same as in figure 4, autocorrelation function. For the segments now created by the successive estimated change point with the offline method. The numbers at the top of every plot are the serial numbers of the earthquakes at the start and at the end of every segment, respectively. Now, the hypothesis of zero autocorrelation in segments can be adopted, indicating that such an analysis is capable to explain initial non-zero autocorrelations. This has to do with the mathematical contribution of this paper, as it is questionable whether we can apply change point analysis in a data set that initially it is not independent. It does not have independent values. In figure 6, we can see maps of the epicentral distribution of earthquakes in the segments suggested by the offline change point analysis on the initial dataset. The starting and the ending point of the segment is noted on the top of the map, while its corresponding time interval is noted in parentheses. It is also shown that during the defined time intervals, the earthquakes in the active periods are in most cases spatially concentrated, while during periods of relative quiescence, they usually exhibit polarity to east and west. In cases G and H, we can discern this behavior clearly, I think. In picture G, we can see this concentration about the main shock, while in picture H, we can see the polarity to east and west. So these are the results I mentioned earlier. Let's proceed to some further results in figure 2, now that we know all these things. The results make the categorization of the aforementioned clusters of increased mean in 4 classes seem reasonable. These classes correspond to time periods 1974 to 1976, 1981 to 1984, 1993 to 1995, and 2007 to 2008. These are the 4 bigger clusters. All these classes are related to discrete phenomena lasting about 1 to 3 years each. They consist of 3 phases, one with increased frequency at the beginning, a period of relative quiescence in the middle, and a notable increase of activity less than the first one at the end of the class. In this presentation, change point techniques were exhibited for the detection of seismicity rate changes mainly, covering parametric and non-parametric techniques, as well as practices that lack hypothesis testing. An application on the theoretical seismicity was also presented, leading to further inference on the seismicity in the area. As far as future perspectives are concerned, Ogata and Turoka in 2016 mentioned that the seismicity anomaly may enhance the probability again of a strong earthquake to occur, and argued that information over the detected changes should be incorporated in the design of the prediction model. Bimodal and Rotondi in 2008 also stressed the need for the probability of an earthquake occurrence to be estimated in connection to the detected rate changes. Online first and quickest detection techniques could also be of great help for online probabilistic forecasting. As change point analysis in seismicity rate has been studied in parallel with stress changes and the spatial distribution of earthquakes, interactions among sub-areas of a selected region could also be studied with respect to change point framework. Next, some references are provided for further discussion. Thank you for your time and attention.
Thank you, Rovi, very much for your talk. We are about half an hour beyond schedule. We can, if there are any questions for Rovi, please type them in the chat, and we can discuss them later on. We can now proceed to the last talk of this session, given by Elisa Varini, and the subject of her talk is comparison of declustering algorithms for modeling background seismicity and analyzing earthquake clusters. Elisa, we can see your screen.
Okay, can you see?
Yes.
Can you hear me? Okay.
Yes, we can see you, see your screen and hear you. Yes, thank you.
I cannot remove this one, and I can put it here. Okay. Sorry, this is the end. Okay, in this talk, we consider the declustering algorithms, because the clustering earthquake catalog is often the first step of many analyses of seismic sequences. And the clustering can be done manually by expert people, but as the catalog are getting bigger and bigger, now it is usually done by applying the clustering algorithm, the automatic method. Several declustering algorithms are available in the literature. But they produce different declustering catalogs, so this can affect the results of the subsequent analysis. Our main goal is now to compare the catalogs declustered by different declustering algorithms. In particular, we consider 2 data-driven declustering algorithms, named the nearest neighbor algorithm and the stochastic declustering algorithm, that also Giancarlo mentioned before. And these 2 methods allows us to identify both the background seismicity and identify the hierarchical structure of earthquake clusters. So now I can give you a quick description of the clustering algorithm that is due to Zagliapin and Denzion. The nearest neighbor declustering algorithm is based on the nearest neighbor distance between 2 events, I and J. And this distance is the product of 3 components. The first one is the inter-event time between the 2 events. The second term is is a term that depends on the fractal distribution of the epicenter, so the spatial distance between the two events, and the third term depends on the magnitude of the first event, the one that probably triggered the second one in some sense. And the idea is that to associate event I to event J if they are very near the nearest one. In this way, we connect each event to its nearest neighbor events. If we plot the distribution of the nearest neighbor distances between couple of events, we obtain a bimodal distribution. This, and we can, the interpretation of this bimodal distribution is that mod, the group on the left, this group is due to the very close events, probably belonging to cluster, earthquake clusters. And the second group on the right probably is due, represents the events that are not so close and probably come from the background seismicity. This can be seen also by splitting the nearest neighbor distance into components, one that include only the time component and another one that include only the spatial component. And we can see the same this plot that represents these two components of the nearest neighbor distances for each couple of events, and we identify the two groups, probably the background and the clustered events. So to split these two groups, clustered event and Poisson and background event, we can put a threshold and separate and identify them. The threshold is estimated through as the point that in which two Gaussian distribution fitting this histogram meets. So through the threshold, the events that are above the thresholds, the events whose nearest whose distances is below this threshold are removed from are removed. In this way, we can find a cluster of events. And the background events are represented as the main shock in each cluster, the largest event in the cluster. We apply this algorithm to a catalog from the northeastern Italy. And this catalog starts in 1977 until now, and we consider events larger than 2 are about 4,000 earthquakes, shallow earthquakes, and the characteristic of this region is that in the last 40 years, the region is dominated by a moderate seismicity, but we know from historical earthquakes that this region can be affected even from stronger earthquakes. Here the representation of the data, the cumulative number of earthquakes and the plotted magnitude versus time. And here we apply the nearest neighbor algorithm. We have the plot of the histogram of the nearest neighbor distance, and we establish a threshold, estimate the parameter needed, and we decluster the catalog. The second, the clustering algorithm we consider is called the stochastic clustering, and Jean described you before. It's based on the ETAS model, which is a special temporal point process defined by two components, one driving the background seismicity and one driving the triggering effect. So through this model, we can define the probability that each event belongs to the background seismicity or it is triggered by a previous event. By simulating from these probabilities, we can decluster a catalog. Of course, we can obtain many declustered catalog by simulation, and in the following we choose the most probable declustered catalog. This is simply the algorithm of simulation. Of course, the algorithm estimated the ETAS model parameters that in our application are this one. This is an output of the stochastic declustering. Here we have the total rate in the region. In this part, the probability that the area that where probably a cluster will occur, and here a representation of the background probability associated to each event. So we have many events that probably are background when this probability is close to 1, and other events that probably are not background because their probability is close to 0. And here a summary of the two declustered catalog by nearest neighbor and the stochastic declustering in terms of number of background events identified, number of clustered events, number of single events, number of cluster, and aftershock and foreshocks in terms of number of earthquakes that occur before the biggest earthquake in the cluster or after. And the results are quite consistent, different but quite consistent. So our first aim is to compare the background systemicity obtained from the two methods. We want to verify if the background seismicity follows a stationary Poisson process, and if it's possible to characterize the temporal changes of the background seismicity if this hypothesis is false. So here we represented our northeastern region, here the full catalog. On the bottom, the declustered catalog, the background seismicity from nearest neighbor, and the background seismicity from the stochastic declustering. Here the plot, the cumulative distribution. Of course, this line becomes more straight. And then we perform some tests to check the Poisson hypothesis, in particular the run test for randomness, the Kolmogorov-Smirnov test for the daily number of background events, and also for the increment times. And we check that the Poisson hypothesis is rejected in both cases. So we think how to model the background seismicity because it's not Poissonian. And so we thought to Markov modulated Poisson process that are double stochastic process in which a Markov process with finite state drive several Poisson processes which generate the earthquakes at a given rate. So we have many possibilities. We estimate first the stationary Poisson model, and then we try the Markov modulated Poisson process by assuming 2-state, 3-state, 4-state, and so on. And for our region, we found that the best model, according to the BSC criterion, is the 3-state Markov modulated Poisson process. So we can represent for the NN declustered catalog and the stochastic declustered catalog the probability that each event occur in one of the 3 identified states of the Markov process. And so we have this plot, and we see on the top the most probable sequence of the 3-state Markov model. And in particular, state 1 is associated to the largest Poisson rate, and state 2 to an intermediate Poisson rate, and state 3 to the lowest one. So we can notice this period that is identified by both algorithms as the most active, and at the same time, in the same way, also there are similarity in the identified sequence of states. Okay. Through this, the Markov modulated Poisson process, is also possible to know the probability that the system jumps from one state to another and how long it stays in each state, an average sojourn times. Then we skip to a second aim, because as a byproduct of the clustering algorithm, we also identify clusters of earthquakes and link between events that define the hierarchical structure of the cluster. So we want to measure the hierarchical complexity of the clusters identified by the two methods and characterize the common feature among clusters. As an example, I consider the cluster identified by stochastic declustering and Eastern nearest neighbor, which include the the strongest events occurring in the catalog in 1998 with magnitude 5.6. This is the spatial distribution of the identified clusters. We can notice that stochastic decluster is more concentrated in space with respect to nearest neighbor. And we notice this also for other couple of clusters. On the contrary, the stochastic declustering tends to include in the cluster events that occur far in time with respect to the nearest neighbor. And the red dots are the points that are not included, are in one cluster but not in the other one, the difference between the two. Then we can also exploit the hierarchical structure established by the declustering algorithms and represent each cluster through a tree graph. On the left, we have the tree graph of the same event as before, identified by stochastic declustering, and on the right by nearest neighbor. We can see that the hierarchical structure of stochastic declustering is in general more complex than the one identified by nearest neighbor. And how to measure this complexity in trees, in the tree graphs? We thought to borrow some measure from network theory, and in particular we choose two simple measures, centrality measure, named Au degree and closeness centrality. For each earthquake node of the tree, we can define an Au degree value defined as an average number of direct descendants. In the same way, we can define for each node a closeness value, centrality value, defined as the reciprocal of the average distance of the node from the other nodes. Both centrality measures range from 0 and 1. Then we can summarize all centrality value according to a degree and closeness centrality of the tree in a global index named centralization. So we define the centralization of the tree, of the global tree, based on the previous value, according to our degree and centrality. We notice that centralization is still a score that ranges between 0 and 1, and we notice that when the score is close to 1, the tree is more simple. I mean, there is one earthquake that triggers all the others as direct descendant. While when the score is much less than 1, the complexity of the tree becomes larger, greater. So we compare the cluster identified by both algorithms and associate a nearest neighbor cluster with the cluster, the stochastic decluster, which have the same larger events. In this way, we calculate centralization value of each cluster, and we compare in this plot. We can see that quite systematically, the nearest neighbor centralization value are greater than those obtained from the stochastic declustering clusters, both for degree and for closeness. We also noticed that there is no spatial, no particular spatial correlation between among the distribution of the centralization value. These are the epicenter of the cluster, the largest events in the cluster, colored according to the degree centralization and closeness centralization. And the distribution is quite sparse. Then we wonder if the results we obtain are special for our region, for northeastern Italy, or can be extended to other regions. So we have some preliminary results on the study of an INGP catalog, an Italian catalog, that extend along all central Italy. It's a large catalog with magnitude at least 2 between 1981 to 2017, and we have more than 4,000 earthquakes. And many earthquakes, stronger earthquakes occur in this region during this period. This is the cumulative number of events with respect to time. Of course, we apply the nearest neighbor algorithm and the stochastic declustering algorithm to this data set. And here we compare the number of background events, of cluster events, and so on, and are quite consistent. Then we compare, we consider the declustered catalog by the nearest neighbor and the stochastic declustering. We check that the Poissonian hypothesis is rejected, so we start to fit the Markov modulated Poisson process with 2, 3, 4, 5 states, and we found that the stochastic declustered catalog the background seismicity obtained from the stochastic declustering catalog is well modeled by a 3-state Markov modulated Poisson process, while for the nearest neighbor declustered catalog, the best model is the 4-state Markov modulated Poisson process. As before, we can compare the probability to be in each state. We look at the top of each picture, and we can find some consistency. The lowest Poisson rate is observed in the first part of the catalog, maybe due to a sort of incompleteness for this period, we don't know. We have to look more inside on this. And then we can see a high rate during the period between 2002, 2008 to 2005, and then intermediate rate, Poisson rate, for the remaining of the time. Of course, as before, we can estimate transition probability from the state identified and the sojourn times in each state. These are an example for an event in an earthquake in the catalog of magnitude 5.4. This is the clusters identified by the both method and their Aldi degree value. Of course, as before, we obtain the same results that nearest neighbor cluster have Aldi degree centralization higher than SRD cluster, and the same for closeness. So some consistency with the result obtained with the other region. And these are the conclusions. The Markov modulated Poisson process is used to assess heterogeneity in temporal pattern of the current seismicity rate. The nearest neighbor approach provides simple and effective data-driven tool to study the internal structure of sequences. And the stochastic clustering approach provides probabilities associated with link of the cluster structure. It provides much more complex internal structure for cluster, reflecting the multi-level tree property of the ETAS model. The centrality measure from network theory allow for robust estimate of a cluster complexity and for identification of most significant events within a cluster. They may provide a new insight of seismic sequences and their evolution. And this is some references. Thank you very much.
Thank you very much, Elisa, for your talk. I have a very quick question.
Okay.
When you identified the cluster with the NN method, we know in general that the NN method, when identify clusters, the cluster identified have long durations containing events far in time from the time when the main events in the cluster occur. So, did you somehow deal with this property in your analysis?
With respect to stochastic clustering, I checked the contrary.
Yeah, I was surprised to see actually. I was
at least in this application, for this region. I don't know about these properties that you are saying, but I will go through in my next analysis.
For example, I've noticed this in Greece. And
really?
Yes, and also in a publication, I read it also in a publication of Antonella for a case in Italy, where when the NN method identified clusters, then there were events that that were far away in time than the time of the occurrence of the main events in the cluster. And I was surprised to see that the difference in your application, and I wrote the question before the slide.
But for example, in this for these earthquakes, this cluster, you can see that both identified almost 3 years of clusters.
Yeah.
2 years and a half. Only that the only difference is that the stochastic clustering identify more earthquakes far in time with respect to nearest neighbors, but both quite long. And probably the difference is with respect to the Windows-based method, the clustering methods, because you fix also a temporal limits for the duration of the cluster.
Okay, I see. Thank you very much. Thank you very much, Elisa.
Thank you. Can I disconnect? Yes.
Yes. So now Dimitris Karlis is going to...
This is the end of the first session.
Yes.
So since we are short in time, let's go to the session 2. So the first speaker will be Renata Rotondi, talking about analysis of temporal variations of seismicity through non-extensive statistical physics. Renata, the floor is yours. We cannot hear you if you talk.
Okay. Can you see? Do you hear me?
Yes, fine. We can see your slides. Please go on. Thank you very much.
I thank you, first of all, I thank the organizer for inviting me to present this talk about a joint work with Gianni Bressan of the Italian National Institute of Oceanography and Geophysics in Udine, and Elisa Varini, my colleague of CNR IMATI. So our goal in this work is to find a descriptor of seismicity activity that acts as a measure of the level of criticality of a system. In this way, significant variation of this quantity could be associated with changes in the state of a system. In recent studies, the earthquakes generation process is described in terms such as phase change, seismic cycle, intermittent criticality, and so on, according to which a region alternatively approaches and moves away from the critical state. In this context, the Earth crust is considered as a complex system characterized by long-range correlation, fractal behavior, multi-level structure, and all features require to be analyzed through new methods inspired from statistical physics. An example of this generalization is given by the new definition of entropy given by Tsallis in 1988. This generalization focus on a particular property of classical Boltzmann-Gibbs entropy, the additivity. In effect, classical Boltzmann-Gibbs entropy has some properties like non-negativity, is concave, is additive. That means that the entropy of the sum of two independent systems A and B is equal to the sum of their entropy. On the contrary, the Tsallis entropy given by this particular relationship, this formulation, where depending on the parameter Q called entropic index, that, as I say, the Tsallis entropy is not additive. That, on the contrary, the Tsallis entropy of the sum between two independent systems A plus B has this expression with this additional term depending on the parameter Q. In particular, when the entropic index Q is less than 1, we speak of superadditivity. And on the contrary, if Q is larger than 1, we speak of subadditivity. When Q parameter tends to 1, the entropy, the function, reduces to the classical Boltzmann-Gibbs entropy. In other words, when Q tends to 1, the system tends to the critical points. We note another one, just I forgot just. I noted that in physics, only in exceptional cases, additivity and extensivity are different. In general, these two concepts, additivity and extensivity, overlaps. Therefore, in our context, we use these two terms interchangeably. According to the max entropy principle, the probability distribution that best describe a phenomenon has the maximum entropy. Therefore, we look for the distribution F, the density F, that maximize the Tsallis entropy under some very simple constraint. The first constraint, called the normalization condition, just means that F is the density. And the second constraint means that the density has a finite Q expectation, where Q expectation means average evaluated with respect to this particular density FQ called escort distribution. To do this, to maximize the Tsallis entropy, we have to maximize the functional phi of the unknown f function and lambda 0, lambda 1 Lagrange multipliers. In other words, to solve the equation, we solve the equation obtained by setting the partial functional derivatives with respect to the f function equal to 1. So, after some algebra, some calculation, we obtain two power law distribution for our variable, in particular fx of the first version of this q exponential distribution is in the case sub-additive. Q, the parameter q, varies between 1 and 2, and the domain function is defined on the positive real line. The second version corresponds to the super-additive q exponential distribution. Q is less than 1 or larger than 2, and is defined over a finite domain. So these are some constraints depending on the calculation. And we note in particular that the sub-additive q exponential distribution in red is a special case of the generalized Pareto distribution. Now we move in seismological context. To exploit this distribution in the seismological context, we recall the fragment asperity interaction model used by Silvan and other colleagues. According to this model, the relative motion of two fault planes can be hindered by the overlapping.
Please, okay. You are muted, Renata, you are muted.
Yes, I'm sorry, I apologize. It's my fault. Just give me 1 second. Renata, can you please, I was hearing a background noise, so I thought I should mute the microphone, and let me find Renata again in my list. Can you please, Renata, unmute your microphone?
Yes, thanks.
I apologize for the interruption, sorry.
Okay, we can't hear you now, I think. No, we can't.
Yes, we can hear you now, thank you.
Can you hear us? Please go on. You are unmuted now. You are not muted anymore.
Okay.
Okay,
can I go on?
Yes, yes, please.
Okay.
Sorry for this.
I'm saying about some words about the fragment asperity interaction model. According to this model, the relative motion of two fault planes can be obstaculated, can be hindered by the overlapping of their irregularities and by the fragments filling the space between the two planes. So following this model, the energy release during an earthquake is supposed proportional to the volume, the characteristic volume R3 of the fragments. We have this expression, X is equal to energy over A, where A is the proportional constant between energy and volume, to 2 over 3, where X is the random variable modeled according to a Q exponential distribution. Another classical relationship in seismology is the links energy in logarithmic scale with the moment magnitude. and that is this one. If we combine these two relationship, we get an expression which link the variables x, that is the characteristic surface quantities, with the moment magnitude. Oh, sorry, some problem. Oh no. Okay, that is okay. So if I replace, make a variable transformation in both two co-exponential distribution, I get this expression for the subadditive distribution of the magnitude. In the case of Q varies between 1 and 2, and where M0 is the threshold, the lower bound that guarantees the completeness of the catalog. In the following, I'm going to talk about the Bayesian estimation of the parameter. Here, I anticipate that to make easier it is suitable to reparameterize the distribution in terms of theta and beta parameters. In the other case, for superadditive co-exponential distribution, I get this expression for distribution of the moment magnitude, but this distribution is defined over a finite domain. Again, I reparameterize the density according to theta and beta, and I note that in this case theta is positive real value, has positive real value. On the contrary, beta can be also negative, can also takes a negative real value. Okay. I stress in particular that considering that the domain on which the density is defined as include the maximum observed value of the magnitude, the density is subject to this constraint, and this is particularly important because this constraint has particular effect on the estimation algorithm. Just a sketch, a very brief sketch about Bayesian estimation. If I take eta, the parameter vector, to be estimated in the Bayesian framework, we assume that the parameters theta and beta are random variables, and we are interested to evaluate the posterior distribution of each parameters, from which calculate the quantities of interest like mean, variance, quantiles, and so on. In general, to obtain the posterior distribution is needed to make complex intractable numerical integration. To avoid these difficulties, we resort to an iterative sampling Markov-Chain Monte Carlo method. In particular, we used the Metropolitan algorithm. The key elements of the Metropolitan algorithm are the choice of a suitable proposal distribution from which to draw a new candidate, new tilde, at each iteration, and the second, the acceptance probability, on the basis of which to decide whether to accept or reject eta tilde at each step. Okay. As probably everyone knows, the main elements in Bayesian estimation are the assignment of prior distribution for the parameters and the evaluation of the posterior distribution. In the case of subadditive co-exponential distribution, the parameter, I can assume that the parameter theta and beta are independent. So the Markov chains are generated separately, that is through component-wise updates. The proposal, the prior distribution chosen are both log normal, and the proposal distribution chosen are again log normal, depending on the current value theta I minus 1 and beta I minus 1 if I am in the ith iteration of the simulation. These constant are calibrated through pilot runs of the estimation algorithm in order to get optimal acceptance rates between 25 and 40% values. In the other case, in the case of the super additive co-exponential distribution, the two parameters are dependent, because you remember that there is a constraint on linking the value of the parameter and the maximum value of the magnitude of observed magnitude. Sorry, I've forgotten a brief note. In most applications, also in other scientific fields, the Q parameter takes almost always a positive value around 1. Therefore, we limit ourselves to analyze the case where Q is between 0 and 1. But very easily it's possible to generalize to this fact, and just considering instead of a log normal proposal for theta, a normal proposal. Okay. In our case, just you see that the prior in this case is log normal for theta and normal for beta. The proposals are the same, log normal and normal, but I stress that the normal proposal distribution for beta depends not only from the current value of the chain, the Markov chain, but also on the candidate value theta tilde of the Markov chain simulated for the theta parameter. And this normal is truncated is left truncated on this interval. We know, in other words, in this case, the Markov chain generation follows a block-wise updates. We stress that the more dependence there is between parameters, and the more efficient will be the update them jointly. In this case, the convergence of the Markov change is quicker, is faster.
Renata, since we are out of time, I mean, can you wrap up a little bit, because we are more than 20 minutes now? Thanks.
Sorry, I can't hear you.
I mean, okay, you have 3 more minutes, because we are already 21 minutes talking.
Okay,
because
okay.
we are very far away from our schedule, sorry.
Okay, sorry. Just I show you the results obtained analyzing data covering 4 years and a sequence of earthquakes occurring in a region around the epicenter of strong L'Aquila earthquakes. I just briefly move from this slide. Here I give you the condition according to which I have chosen this particular space-time in which to analyze the magnitude. And in particular, I stress that to investigate in detail the temporal variation of the Q index, we have analyzed time windows of 100 events shifting at each new event. We have followed, we first fit both the Q exponential distribution to the data in each window, and then compare the values of their posterior margin log likelihood, where theta j and beta j are the Markov J chains generated through the Metropolitan method. Inspired by the bias factor, we have compared the discrepancies between the three models, and I have chosen this kappa value, which indicates strong evidence in favor of the first model with respect of the second. So looking at this, in this table, partition contains the partition, the time windows, and you can see immediately that the sub-additive Q exponential, Q larger than 1, provides the best performance in the large majority of the cases of the windows. And the only 92 windows in which super extensive distribution performs strongly better are concentrated in the 4 hours immediately after the main shock. Just to give a look to the different shape of super extensive on left and the sub-extensive density in the windows where these two distribution performs best. And here the most important result, in my opinion, this picture collect the estimate of the Q index and associated to each time window, and I stress that each parameter reports the same number of index. So in order to more clearly show the results. But consequently, each panel covers quite different time period. For example, the first panel covers 2 years, and then the second 3 months, and the other panels cover just 2 days, and so on. The vertical lines denotes the occurring time of the stronger events, and the horizontal lines in solid line, the mean, and in dashed line, the first and third quartile of the Q indexes. So we can, probably it's better to look at the picture. So we can easily observe that the strong events are often preceded by a lower Q value, here, and so on, and followed by a jump, by a sudden jump, by an increased Q value. This behavior is especially evident for the main shock, both in the time duration, some years, so some months, sorry. The red panel contains the main shock, and in the size of the variation. The largest fluctuations are observed in the first 3 days of the after sequence, corresponding to these panels, the 1, 2, with these 5 panels, and after the last events of magnitude 5, the curve substantially returned to within the interval of first and fourth quartiles. Okay, just to say, we suggest that the feature with the highest forecast value are those that are most persistent, in our opinion. This is just a picture about the estimate of the entropy. This on top is a zoom on the main shock, and you can observe also in this for the entropy the same behavior, decrease of the entropy before in the month which precede the main shock, and a sudden large increase after the main shock. So in conclusion, the Q index decreased before an earthquake of middle to high magnitude and increase suddenly after it. Both the duration and amplitude of this effect depend on the magnitude of the shock. As for the Q index, the entropy shows a significant and persistent decrease before the main shock, which indicates energy concentration, followed by a sudden increase that corresponds to energy dissipation. Our future research topic could refer to the analysis of other features of the earthquakes. For example, when and where they occur. That is, we propose ourselves to study the interval time and the spatial distribution of sequences of earthquakes. Thanks for your attention.
Thank you very much. Since we are half an hour off, I propose to have questions at the end of the session. So we move to the next speaker, Antonella Perezan. She's going to talk about quantifying the time-dependent features of seismicity in northeastern Italy. Thank you.
Thank you so much. I hope you can view my slides.
Yes, we can
full
see
screen.
your slides and we can hear you. So
Perfect.
go on. Thanks.
Thank you. So I will go very empirical compared to what Renata Rotondi was explaining so far, and I will just connect to what were a conclusion. So addressing the aspects of interval times and especially the space and time features of seismicity, and I will be dealing with data that were already presented by Elisa Varini, namely the catalog of northeastern Italy, which will be analyzed by the unified scaling law for earthquakes and other classical parameters like bending of strain release and inter-event times. So just to provide, let's say, an overview of what I would like to address during this talk is that, well, in any statistical analysis of seismicity, there are elements, a priori information, which are not, let's say, not non-stochastic elements. So whenever you wish to apply a statistical model, you need first to define the area and the time span, and then you have to assess the data quality, which may in turn affect the selection of the area and the time. So these quantities are all interrelated. One of these elements, however, I believe it's very important, and it is the a priori definition of an area, because the selection of the area where to investigate seismicity, where to apply the statistical model, permits to incorporate additional information which is not included in the seismicity itself. And it could be some geodynamical, geophysical, or other geological information about the area that can be used to select the area for the analysis. And this may help, as we are going to see, to disclose some features which would not be visible otherwise when we mix up areas with different features. So what I will try to show you is a kind of a multi-parametric empirical analysis of seismicity, which refers to the seismic districts of northeastern Italy that have been defined based on geological and geophysical information. So just a few words about the area and the catalog. The data which I'm going to use are consist of the OGS bulletins, namely a catalog which covers northeastern Italy and surrounding areas like Slovenian territory. The catalog includes about 30,000 events for a time span of about 40 years now. And well, the area was affected by a large earthquake in 1976. And since then, in this territory, only moderate to low earthquakes were recorded. The two largest events took place in an area between nearby the borders between Italy and Slovenia, namely in Kobarid, one in 1998 and the other one in a very close location in 2004. The catalog, we investigated in a preliminary way the catalog, and in particular we defined the territory of completeness for this data set. And you can see here this red polygon outlines the territory where the catalog can be considered complete for magnitude from 2 and above. And this information was obtained by comparing the bulletins with the global data sets. And you can see that outside this polygon, the information from the global catalog is larger than the one provided in the local data set. Within the completeness territory, the information in OGS bulletin is much more complete and, let's say, provides many more earthquakes. So we apply to this data the unified scaling law for earthquakes, which is a generalization of the Gutenberg-Richter law. which includes a term, an additional term, that permits to account for the non-uniform distribution of epicenters in an area. And here in this relation, you see we have a term which accounts for activity, like in the Gutenberg Richter. This B corresponds to to the B value, and this C corresponds to the fractal dimension. This is the correlation dimension between epicenters in the area. The scheme of box counting, which is applied to compute the parameters for the unified scaling law for earthquakes, this is called telescope, and it starts from a large territory and then it zooms down to smaller territories, and also accounts for rotation of the area, so as to consider all possible configuration in the territory surrounding a small cell. Then all this information is associated with the smaller scale cell. Sorry. In this way, we could compute for the territory of northeastern Italy these maps. These are the coefficients estimated for cells of size of 1/16 of degree. The largest scale of the hierarchy is 1 degree, and then we scale down to 1 to 16. So from about 100 kilometers down to about 7-8 kilometers, more or less. So we can see from these maps of the parameters activity, B value, and fractal dimension that there is quite a heterogeneity over the investigated territory. And also we compare for these areas the values we received with the unified scaling law for earthquakes with classical estimates of fractal dimension and B value, and we found that they are really consistent on average. But with the unified scaling law, we can get more detail, and we can see this heterogeneity. Here, I wish also to recall something that was presented by Elisa Varini in her talk, and I wish to stress that also from point of view of spatial pattern of earthquake clusters, we have some heterogeneity, at least for clusters identified by the nearest neighbor approach. We could find that in this area, along this, let's say the separation between the Po Plain and the Venetian Alps, we have a large number of swarms, whereas in this part, where there is a dynamic trend, the earthquakes tend to occur in burst-like sequences. To explain a bit better, in this area to the west of the region, we have swarms, long sequences, whereas in this, let's say to the east of the study area, we have largest events, but they have, let's say, we have the main shocks and classical aftershock sequences. So also we have seen in this way that we have heterogeneity in space from the point of view of parameters of seismicity and also the way the energy, seismic energy is released. So we decided to investigate a little bit better in more detail to select some sub-areas to see whether we can uncover some features that are possibly hidden in when considering all territory together. So we consider the area of completeness, and we consider that seismic districts of Friuli Venezia Giulia region that were independently defined based on geological information. And you see these areas are pretty small, and seismicity in some of them is really limited, where you can see from this map the density of epicenters. Here you can see the epicenters and the three regions we outlined, separating areas with different geological tectonic features. And you see here, these are the three areas that we selected. One corresponds to the eastern southern Alps, the other corresponds to the outer Dinarides. And here it is a junction area which is characterized by very high fragmentation and also seismic activity. We assess the completeness within each of the areas, and we found that they can be considered complete for magnitude 2 and above, at least since 1995. And using this information within individual areas, we computed again the coefficients A, B, and C for the unified scaling law for earthquakes. And again, we can see that the values we obtain, especially when we deal with the fractal dimension, are very different in the three areas. And for these values, we also perform statistical tests. For instance, we applied the Kolmogorov-Smirnov two-sample criterion, and we found that the distribution of parameters within the three regions, A1, A2, and A3, are statistically different in statistically significant way. The minimum is 95% of probability that we are able to reject that they are coming from the same distribution. So given that the territory makes a difference for the parameters, then we go and investigate the temporal variations of seismicity within the identified subregions. First of all, we analyze the classical parameters such as the inter-event times. You can see here the distribution over time that is computed considering groups of 50 events. And we can see that, for instance, the region A1, which is the one located to the west, where we have the swarms, where we have low seismic activity, is pretty stable over time. Whereas the seismicity in the region A3, which is located to the east, where we also experience the largest events, is characterized by much larger fluctuations. These two are the points in time where we have the two largest events in the region, 5.6 and 5.1. But you can see that large fluctuations are observed even in absence of significant events. Actually, here there was a sequence with magnitude 4.9 that maybe triggered this change. We also estimated some intervals of time where we have some uniform trend, and we can see that no trend is identified for A1 region, whereas two intervals are selected for the other two regions. Now let's move to another parameter that we use to quantify seismicity, namely the Benioff strain release, which is proportional to the square root of the energy release. And here we can see that the cumulative strain, the cumulative Benioff strain release displays even much more evident differences in the three regions. Specifically, we can see very clear jumps in the region A3 because there we have the two largest events, while in the A1 region, the western side of the area, we have a trend which is practically uniform all over the time span. So it means in over 25 years, it is very constant in time. The region A2 only experienced one magnitude 4.8 event year in 2002, and we can see a jump and a change in the slope. So what we noticed is that when we have a large event, or large compared to the size, a large event for the region, because we are dealing with magnitude 5 still. So we have a change in the slope of the curve of Benioff strain release. So if we compare the slope of this segment with this steady trend of region A1, and the same we can do here, we notice that corresponding to the largest events, we have a change in the slope. So it means that on the long term, after a major event, the system seems not to go back to the earlier condition, but it seems that it changes in the way it releases the seismic energy release. Well, and that's what I was just mentioning. The slope changes after the occurrence of a rather large earthquake. Here are the figures. I will just skip these, but just some consideration about, just to reconnect with what also Renata was saying. In terms of non-extensive statistical physics, we can speculate that this observation suggests that on the long term, I mean, not before an earthquake or immediately after, but on the long term, the exponent which is associated with the normal state may change after the occurrence of large events. And well, let's see what it happens for the coefficients of the unified scaling law for earthquakes. So here we can see for individual zones, for the individual districts, that actually there are very large or quite large fluctuations of the coefficients A, B, and C. And well, we see that there are regions with a high level of similarity in these variations. This bunch here in red and yellow and brown correspond to these three regions that we incorporated in the zone A3, whereas the other are, let's say, more similar as a time trend, which confirms that our choice, our grouping is quite reasonable. So to capture in a single parameter the variations of the unified scaling law, we use the so-called usually control parameter eta, which is not the nearest neighbor distance eta, but it's a slightly different thing, which is computed considering the inter-event time between two subsequent events, a term which accounts for the magnitude, the energy release, and the term which accounts for the distance between the epicenters, L, and the fractal dimension. Here we can see the fluctuations or the variations over time of the usually control parameter for moving windows, including 50 events each. And also for these curves, the periods of uniform, let's say, stable parameters have been identified. So the slope, the trends of these curves, which identify, which characterize the time periods of, let's say, stable seismicity. And what we notice is that during the last interval of time, so since 2005, no further variations are detected in the three regions, so the seismicity should be stable. And if we compare the overall distribution, probability density functions of the parameters obtained for the overall time span and for the most recent stable time interval, we see that they are pretty different, especially for the region A3. So it looks like that based on the usually control parameter, the recent period of time is pretty peculiar. And we can see it also by investigating the correlation between the different parameters of the unified scaling law. Here in this representation, we can see the B values, parameter B, versus the fractal dimension, that is parameter C, which are computed for different time. So this is for here, for a time window of 6 years ending in 2001, windows of 6 years ending in 2002, and so forth. And so these four plots include the event magnitude 5.6, which occurred in 1998. These plots here include the event magnitude 5.1, which occurred in 2004. So the red dots, which correspond to the area A3, where these events occur, display features that are correlated with these events, at least up to 2010, because the earthquake occurred in 2004. So we can see that the other values remain pretty stable, and also the parameters B and C are quite stable within this area A3 when they are related, they can be related with these sequences associated with the large events. But during the recent period, we see starting in 2011 and onward, we notice that there is quite an interesting trend in the parameters of region A3, which changes in some steady way. And this is worth of, let's say, it's our idea to study in more detail to try and understand why there is this evolution of seismicity, which you see displays a clear tendency, a clear variation during the last about 10 years. And this variation is very evident when accounting for the three subregions defined in this way. So I just come to the conclusions, just stressing that the analysis of these of the coefficients of the unified scaling law highlighted the heterogeneity in space of the seismicity of northeastern Italy, and also stressed the relevance of the importance of using a proper area for the analysis of temporal variations of seismicity. Also, we argue that based on our results, after a relatively large event in a region, the system is not going back to its earlier state, but probably it moves to a different level of seismic energy release. And well, as a final observation, this analysis stresses the non-stationarity of seismic activity at the time scale of years and even decades in the area, in agreement with what was shown by Elisa Varini for background seismicity. And this element, in my opinion, should be taken into account when computing seismic hazard assessment, especially in a local scale, where it is important to account for temporal variability of earthquake occurrence. Thank you so much.
Thank you very much, Antonella. I still think that the questions will be put later on in the discussion because we are out of time. So the last speaker will be Katerina. She's going to talk about using negative binomial hidden Markov models to extrapolate for past states of seismicity. Katerina.
Thank you. Can you hear me? Can you see my screen?
Yes, for both.
Okay, thank you. So our work involves using negative binomial hidden Markov models in order to extrapolate past states of seismicity into the future. In recent years, hidden Markov models have become popular in modeling geophysical data because of the heterogeneity of the data and temporal dependencies that are present in real earthquake sequences. We have applied Poisson hidden Markov models to model sequences of earthquake counts in several seismogenic areas of Greece, like Kyllini, Samos, Zakynthos, and the models were also used to identify temporal patterns of seismicity in Sumatra. Over the years, numerous attempts have been made in order to obtain the distribution of earthquake numbers. The most popular distribution that has been widely used to describe earthquake numbers is the Poisson distribution, due to its simplicity and relative ease of application. Another distribution that has been used to approximate the earthquake number distribution is the negative binomial. However, it appears that for small time intervals, both the Poisson and negative binomial distributions fail to fit observed earthquake frequencies. And so the question that arises is, why is it so difficult to approximate the distribution of earthquake numbers? And what if it's not a single distribution, but rather a mixture? So we are going to try to describe the characteristics of earthquake numbers. Seismicity varies in time and space and depends on the level of clustering in a particular area. Take, for example, in the days following the occurrence of a strong earthquake, extreme number of earthquakes are recorded and high level of clustering is observed both in space and time. During the clusters, the rate increases sharply compared to periods of ordinary seismic activity. So, okay, let's talk about what is ordinary and why the models fail for small time intervals. Earthquake time series have excess number of zeros, especially for small time intervals. And in addition to the existence of serial dependence, the variance of the data is greater than the mean, indicating both serial correlation and overdispersion. So we aim to use negative binomial hidden Markov models in order to provide estimates on a daily basis, as well as on 5-day and 10-day intervals for the expected number of earthquakes in a specific study region. In order to handle overdispersion within its state, we have selected the negative binomial distribution as state-specific probability distribution. In addition, this distribution enables us to handle the excess number of zeros that are present in earthquake time series. And the region of Kyllini, Western Greece, has been selected to apply the proposed methodology. So a hidden Markov model consists of two parts. The first part is an unobserved sequence of states denoted by CT that consists of a Markov chain, and each state is associated with a probability distribution F from the same parametric family. The second part of the model is a non-negative integer valued sequence of random variables y1 to yt that conditionally on CT are mutually independent. So when the state of the model at time t is known, then the probability of observation yt is fully specified by this quantity. So the selection of F may be either continuous or discrete. In this presentation, we focus on discrete valued hidden Markov models, and F may be selected among different parametric families. In our application, we have selected the Poisson and the negative binomial distribution. We use a parameterization of the negative binomial distribution in which the probability density function is expressed in terms of the mean and the same parameter. And in this parameterization, the variance is a quadratic form of the mean. And you may observe that when the same parameter tends to infinity, then this term tends to 0 and the variance tends to the mean. So the negative binomial distribution tends to the Poisson. So in hidden Markov models, the parameters are the transition probabilities of the Markov chain denoted by gamma ij. And this is the probability that given the hidden process was in state I yesterday, it will be in state j today. And of course, the parameters of the probability distributions. So however, even if the parameters are known exactly, the model is still hidden. And what we can do is we can estimate the probabilities that the observed outcome is generated by each one of the hidden states. They are also known as state probabilities. This is the definition of state probabilities. It's the conditional probability of occupying state I at time t, given the whole observation sequence. So the state probabilities are estimated through the backward and forward probabilities. I'm going to skip the mathematical details, and I'm going to proceed with giving you the outline of what needs to be done in order to produce forecasts. First, we need to find the optimum number of states of the fitted models using model selection criteria like the Bayesian information criterion. And then we need to estimate the model parameters using an expectation maximization algorithm. The next step is to find the unobserved Markov chain using the Viterbi algorithm. And finally, conditionally on the process being in a given state today, we estimate through simulations the number of earthquakes expected to occur tomorrow in the study area. And in order to proceed, I'm going to describe you some, in order to produce our forecast, we have adopted some basic principles. And these are that the data used to estimate the parameters of the model are different from the data used to generate the forecast. And we use a learning period to estimate the parameters, and then a testing period is followed in which the forecasts are generated. And finally, the forecasts are generated beyond the end of the estimation period. We do not update the parameters as we move forward in time. And during the testing period, the forecast is made at the end of the day, at which time the probabilities of the process being in any given state for the day following are known. The next day, the state probabilities are updated to include the most recent information, and the process is repeated. So the methodology was applied to the area of Kyllini, Ionian Greece. This is the area of study. The test area is situated on the narrow inner shelf of the northwestern side of the Hellenic Arc, occupying the strait between the island of Zakynthos, this is Zakynthos, in the Ionian Sea, and the Kyllini Peninsula, northwest of Peloponnesus on the Greek mainland. This is part of the continental side of the plate boundary segment where the Mediterranean lithosphere moves from southwest to northeast towards the Eurasian plate and subducts beneath it. The time interval from 1990 to 2004 was used as a learning period, and all earthquakes with events with local magnitudes greater than 3.2 were selected, and the events were counted in time intervals of 1 day, 5 days, and 10 days. So this is the daily time series of earthquake counts. The number of earthquakes is plotted for the learning period. So this is the number of earthquakes is plotted versus time. We see in this figure that there are 3 clusters. The first and the third cluster correspond to 2 earthquakes that occurred in our study area on the 26th March of 1993 and 2 December of 2002, with moment magnitudes 5.6. The cluster in the middle corresponds to the aftershock sequence of a very strong earthquake that occurred outside of our study area in November 1997 with moment magnitude 6.6. The aftershock sequence of this earthquake extended within our study area and affected our time series. So some descriptive plots of the data for the case of the 1-day interval, we see that you may observe here that the number of zeros in the time series reaches to a number up to almost 5,000. So the number of zeros dominates. And from the autocorrelation function plot, we can see that there is evidence of serial correlation in the data. We applied in the model both Poisson and hidden Markov models and negative binomials with different number of components. And based on the Bayesian information criterion, the model that best fits the data is the negative binomial hidden Markov model with 3 states. And these are the parameter estimates for both models. Please observe here that the 3 states of, in the case of the 3 states of the negative binomial hidden Markov model, the second state has a very high value for the shape parameter. It is the state that has the lowest mean value, and this state shows Poissonian behavior. The other 2 states seem to follow the negative binomial distribution. So we estimated the unobserved sequence of states that underlies the data for the negative binomial hidden Markov models, and we can see here that the 3 states of seismicity. State 1 is the state with the highest mean and corresponds to high seismic activity. State 2 is to remind you, is the state that has the lowest mean and corresponds to very low seismic activity. This is a state that has that tends to the Poisson distribution, and we have also state 3 is a state that corresponds to moderate seismicity. So these are the data in the testing period, the data we want to estimate the expected frequencies. They cover the time interval of from January of 2005 until the end of December of 2007. It is The duration is of 3 years, and we may observe that in the middle of April of 2006, 2 earthquakes of magnitude 4.8 and 4.5 occurred with a time difference of 3 days. This resulted in this cluster of earthquakes reaching to frequencies up to 9 earthquakes per day. So through the best fitting model was used to estimate through simulations the number of earthquakes expected to occur in the study area for the daily time interval, and we see that the expected frequencies have higher values during this cluster that appears in the mid of April. And also we estimated the unobserved sequence of hidden states that underlie the data for the data during the testing period, and we can see again that to the cluster in the mid of April is associated the state of high seismic activity. And some simulation results, we simulated data according to our best fitting model, and then refitted the models to the simulated data. And these are the box plots of the parameter estimates we obtained from 1,000 simulated samples. And some descriptive statistics for the 5-day and 10-day time series. The plots on the left correspond to the 5-day time series, and the plots on the right correspond to the 10-day time series. You may observe that in the case of the 5-day time series, the number of zeros is about 500. To remind you that in the case of the daily time series, the number of zeros was about 5,000. While in the case of the 10-day time series, the number of zeros is about 250. Of course, as the time interval increases, we have less counts in our resulting series. And from both autocorrelation function plots, we can see that we can see the evidence of the presence of serial correlation. So we have applied both Poisson and negative binomial hidden Markov models for the 5-day time series. And again, the model with 3 components was selected for the negative binomial hidden Markov model. And similar is the case for when we applied our model to the 10-day time series. And these are the parameter estimates these are the estimates of the parameters of the negative binomial distributions for the best fitting model for the 5-day time series and the 10-day time series. You may observe that the means of the negative binomial distribution are for the 5 days time series are double than the means of the negative binomial means in the case of the 10 days intervals. And some simulation results, again, for the parameters of the models of the model for our best fitting model that correspond to the 5 days data, and similar is the case for the 10 days data. And finally, the expected number of earthquakes we obtained through simulations for the 5 days data and the 10 days data. Observe that in both cases, the expected number of earthquakes increases during the cluster that appears in our data in the mid of April. This is the similar case. This is the case in all 3 time series. So in all 3 cases, the negative binomial hidden Markov model is able to extrapolate past states of seismic activity into the future by capturing the future variations of seismic activity. Regardless of the time unit we select, in the case of the negative binomial hidden Markov model, 3 states are selected, and the 3 states correspond to very low seismic activity, moderate activity, and increased seismic activity. In our application, the data in the testing period and the data in the learning period have common features. So if the data in the testing period had totally different characteristics to the data in the learning period, then our forecast would definitely fail. And the out-of-sample forecasting based on hidden Markov, negative binomial hidden Markov models is encouraging. However, the use of covariates in the parameters of the models to allow for additional information would further improve the results. And these are some references. Thank you very much for your attention.
We thank you, Katerina. So let me wrap up this session. Since we didn't have any questions, perhaps now is the time for questions for all the speakers. There is one question for Katerina. I read. Did you check the distribution of sojourn times for each state?
No, I haven't, but I can tell you for sure that states of low seismicity dominate.
Okay. Other questions for all three speakers of this session, please?
Can I do a question?
Of course.
I would ask Katrina, why do you think that negative binomial has a better performance with respect to Poisson in this case? Which is the properties of this distribution?
Yes, I think that the negative binomial is able to model also the differences that are observed between earthquake counts within each state. Something that the variation within each state, something that is not possible with the Poisson distribution, because it allows the over dispersion. I think that's the property of the negative binomial distribution that makes her more better than Poisson.
Okay, thank you. Thank you very much.
Any other question for all speakers? Okay, so I think perhaps we have left some time for this event at the end in order to be able to discuss all together. So I will try to wrap up the day. First of all, I would like to thank Katerina for organizing this. She was the leader, and we, Department of Statistics, helped her to take care of everything. I would like also to thank Mr. Marousis for helping us building up this presence slot today. So I think that we had some nice talks about okay, there is one interesting question. I will put it in the table. So the idea is that we tried, let's say, to have different ideas about statistical and stochastic modeling for earthquakes. So I'm pretty glad that we have seen quite interesting and very different aspects of applied statistics and mathematical statistics applied to seismicity. I think that this collaboration between, let's say, statisticians and those working with earthquakes, seismologists or whatever, it can be extremely fruitful, because I think that the kind of problems and the kind of data is very, very interesting. There is one question to all speakers, and perhaps this is a nice, let's say, question to open the discussion. Would you say that the seismic action in Thessaly is related to the big earthquake of Samos in October 2020? Can you see any relationship on that? Professor Ganas says that the distance is too far, and the physics-based models do not do not see something like that. And also Professor Kuyara says the same. So it seems that we all agree that it is too far away in order to have any relationship. Anyway, so I think that I try to wrap up, and perhaps we have some time for discussion. If there is something that somebody would like to initiate, or Katerina, do you have something in mind? It would be nice to discuss all together now.
Thank you very much, Dimitri. I would like to thank all of the participants, and the ones that attended this webinar. We are ahead. We have run out of time. So if someone wants to put a question on the table or someone wants to discuss something in the end, now it's the time to say it. I would like to thank you all for being here and participate, and the speakers for accepting our invitation, and Thanasis Marousis for all his technical help. So thank you very much.
Okay. We are out of time anyway. We're supposed to end at 1 o'clock, so it is already a quarter past 1. So thank you, everybody. I think that we reached the end of this workshop today. We hope to be able to organize something similar in the near future. I would like to thank very much Renata for their help. Thank you very much.
Thank you. Bye to everyone.